Okay, time to continue. So in the previous part, we ended up here where we've shown that there is no way we can implement a function mul_d which just takes the result from computing the derivative of f and g to compute the derivative of multiplication of f and g. So there is not a homomorphism, but we can define a function there which satisfies the specification. So if we replace mul_d here by mfg, so a new function called m with f and g as additional arguments. So notice it still gets f prime and g prime, so the derivatives, but now it also gets f and g. So as you can see down here, m now has a long type. That's why I've abbreviated funexp to just f here. So it takes the function f, the second function, the first function's derivative, and the second function's derivative. And the primes here are just parts of the name. So Haskell doesn't put any significance to this prime, it's just a name. But it's a useful name because we can more easily remember that f prime here is representing the syntactic derivative of f. Okay, so if we want to fill in this one, notice this is now not a homomorphism because it can't be computed from only the subtrees, and we'll soon fix it. But just to know where we're going, let's fill in this definition. So we know that the multiplication case for derivative should give two terms, so it's an addition, and it's two multiplication cases. And what to multiply? Well, the derivative of the first term with the second unchanged, and the first unchanged and the derivative of the second term. So notice that we've created a syntax tree with an addition and two multiplications. And we really needed to have access to f and g here. So there can be defined as a function in Haskell. It can compute on this syntactic data structure, but it cannot be defined immediately as a homomorphism. And the reason we want to define things as a homomorphism is because then we can, for example, make a type class out of it. We can compute without having to we can compute the results recursively and just put them together at the end. So let's see if we can fix this. So tupling to the rescue, it says here. So remember, we had the semantic type S was functions from R to R, and the syntactic type here, funexp, was F. And we will try now to compute another function, not there, but there too. And the idea here is that, as we noticed in the mul_d case, we needed two values for f and two values for g, or two syntax trees. We noted both. Let's put it a little note here. We needed both the function and, say, with the green, its derivative. So both have the same type. Both are syntax trees of type f. But we can now compute a function there too which returns both. And as before, we have a kind of diagram here where there are two that we want to define. It is defined in terms of, it's specified in terms of the fact that when we evaluate the result, we should get the same as if we evaluated the function, and if we evaluate the second component, we should get the same as the derivative of the function. And we'll get back to the specification a little later. But first, let's say that if we now apply this idea of wishful thinking, or a recursive function of the standard form of fold, then if the whole function should return a pair, that means that from each subtree we should get a pair. And that means that we can now attempt to see, can we solve this problem as a homomorphism if we have subtrees which contain both the function and its derivative. And if we look at the previous slide, that seems promising because here we have f and f prime, and we have g and g prime. So if we pair them up so that here we have f and f prime, and I shouldn't have a dot there. Oops. And then we have g and g prime. So notice these are just names, they could be called whatever, but the f prime helps me to remember that the second component is intended to be the derivative of the subtree. Then we should also produce here a pair. So it's supposed to, well, I said implicitly here that it's supposed to return the same as its input, because we need access to that later, and the derivative. So the first component, this part, should be just the same as what we had on the left-hand side of the definition of dir2. And we haven't seen that definition, but that's the multiplication case with f and g. So we've computed the function and its derivative from further down. We just collect the two first components into multiplication. That's the first component of that type. And then for the second component, that's what we computed on the previous slide. That's this addition of two multiplications. So I'll see it's a little wide here, so I'll try to make the font a little smaller. So it's the addition of the multiplication of f prime and g, and then multiplication of f and g prime, and then the end parenthesis of the pair. Okay, so mulder, the one I had on the previous slide, the little m, is now called mulder with another type. I've sort of paired up the arguments. And we can note, just by the way, that I've used the infix cross here, so the Cartesian product for the notation for pairs in Haskell, which I'll use from the next slide on. The syntax on the type level is parenthesis, comma, parenthesis, but here I've separated it out. Okay, so notice that we can also do this on the semantic side. So the function that's yellow here, the yellow dashed line, that function will need a multiplication case, and it's very similar. It takes f and f prime, but here real functions, g and g prime, also real functions, and then it returns, well, the first component should have been multiplication of f and g, and we actually have looked at an earlier lecture that we can make an instance of multiplicative for functions, so we can actually use function multiplication here. So corresponding to the syntactic case, here we have the semantic case. And that also means that we get a very sort of readable version here. I put parentheses to just make sure that we do everything in the right order. F prime times g plus f times g prime. And then end parenthesis for the pair. So this is just to see that we recognize this is the addition. Here are the two multiplications. If you're unused to the prefix style, then you can recognize more easily perhaps the derivative here. So what is it hinting at, and we will show in some live coding later, is we can actually define these functions in Haskell to compute either the syntactic derivative or, well, the syntactic copy, deep copy and derivative, or the semantic copy, identity function and derivative. Okay, and I think this one just says the same thing as I just wrote. Okay, now if we want to continue to complete the definition of dir2, so notice here I've used the Haskell style. Instead of cross product, I used the notation for pairs in Haskell, pair type in Haskell. So I want to take one syntactic type, syntax tree, and produce two syntax trees. And let's look first at the two recursive cases. So we already filled in mal_dir. So it calls dir2f recursively, dir2g recursively, and remember the type up here, that means that we will get a pair as the first argument and a pair as the second argument, and then mal_dir that we just defined on the previous slide, which now has this type, is doing the computation of both the function and its derivative. And then we just need to complete it with the other three cases. So up here on this slide, I'm adding add_dir at the top. So it has the same pattern matching, f and f prime, g and g prime. And then I just need to return, well, first we should check, we're on the syntax side. F is equal to the funX type, so this would be syntax tree. So this will be the addition of f and g, and this will be the addition of f prime and g prime. So this is the second component here is the law for derivatives of sum. So its derivative is linear. Okay, then we have the two last cases, the leaves in the syntax tree. So, remember add and mul just had two syntax trees below, but at the end we have to end up in either an x or a constant. Okay, so if we want to compute the syntax tree for the function and its derivative, then the first component is just x. So yx, well, we should return actually the same function as the first component to enable, the whole reason for doing that is to enable the computation of the derivative and the multiplication case. All the other cases go through without it. But here, this is the base need, and we have to return our input here. Okay, and the second component should be the derivative, the syntactic derivative of x. Well, derivative of x is const 1. So the const c and then 1. And in the constant case, the first component is always sort of a deep copy, so it returns the same. And then the derivative, which is const 0. Okay, so with this, we've completed the definition of dir2 as a homomorphism, because it has this shape of always calling itself recursively on the two arguments when the subtree is branching. So for example, we notice here that dir2 is a homomorphism from add to add_dir and from mul to mul_dir. So if we want to remind ourselves of what the notation was for this, we have these two predicates. So dir2 goes from add to add_dir. Actually, one d too little there. And the same dir2 is also a homomorphism from mul to mul_dir. Bit of a bad U there in the middle. Okay, so we have managed to produce a definition of the derivative. We haven't proved here that it actually does the right thing, but that can be done separately. So let's see what is, this was the filled in version of the previous one. What was the specification actually? So it's perhaps strange to go to the specification last, but I didn't want to complicate because the specification itself is a little bit hard to read perhaps. So what I'm trying to say here, that if we have syntax trees, f, f prime, and fe, this is the relation that should hold. So if we compute dir2 of a syntax tree, call it fe, it will return a pair. Let's call the first component f and the second component f prime. If we evaluate f, so the first component, we should get the same result as if we evaluate fe. So for example, that can be achieved if it's just a deep copy. But it could also do some simplification on the fly. So there is nothing stopping us from returning an f here, which is not syntactically equal to fe, as long as it would evaluate to the same function. Okay, so that's the requirement on the first component. And then the requirement on the second component. Well, the second component is supposed to be the derivative. So what it says here is if we evaluate f, which, if you remember, is equal to eval of fe, according to the left-hand side here. So if we take the derivative of f or fe, which is the same, if you evaluate fe or f, which is the same, and then we take the derivative, then we should get the same as evaluating f prime. So what it is saying is that the two components coming out should be sort of essentially the same as fe and its derivative. Okay, and this was just a copy of the previous line. But the interesting thing is now, so as we can implement there too, we have implemented a homomorphism which computes more than the derivative. So there too, remember, it computes a pair. And that means we can define, instead of what we tried before as a homomorphism, we can compute there too as a homomorphism and then throw away the first component by composing it with second. So the composition here is not a homomorphism, but it can be computed by a homomorphism and a trivial function. That's all for this part.